Today we will continue our discussions on the single phase induction motor. In the last class, we presented a controversy to you, mainly to clarify what do you mean by rotating field and what is this double rotating field or double revolving field. And this indeed was a serious problem in the initial stages of the development of single phase motors and their analysis. And that is why it was primarily branded as a dilemma of single phase induction motors. So, this was called the dilemma of single phase induction motors, because it was originally who stored this double revolving field concept was Ferraris. Okay. Ferraris, it was way back in 1894. He presented, there is a paper in the journal Electrician. He titled a method for the treatment of rotating or alternating vectors with an application of alternating current motors. Okay. So, it was this which postulated, as we mentioned in the last class, that you can, if you have a 3 phase lines A, B, C, and you have the stator A, B, C phases. Of course, there is a rotor is squirrel cage and a common shaft. He said all you have to do is A, B, C, it becomes A, C, B. Okay. That means you connect, of course, connect properly for these ones, and the same windings you connect in a different way. This is positive sequence, this is negative sequence. Okay. That is what was postulated, which meant that this will spin the machine in one direction and this will spin the machine in the opposite direction. So, the net torque will be whatever, if this produces T1, this produces T2, it will be T1 minus T2, that will be the torque. Okay. And this was what is known as Ferraris model. But this was found to be later wrong. Why? We tried to explain last class. Why was it found to be wrong? Yes? He said this single phase motor was supposed to be equal to this, right. Whatever this motor was producing, the torque or the currents or the heating must be same as this. Because we found out that if you pass a single phase winding, it produces two counter rotating fields in the air gap, and the reaction of the motor will be a cumulative reaction of both the fields. But I explained last time there is some fallacy in this logic. What was the fallacy?
Forward field is not equal to the backward field because the slip is different.
Yeah, forward field is equal to is not equal to backward field because if a different slips, reaction of the rotor to the forward field will not be same as reaction of the rotor to the backward field. So, rotor gets magnetized differently at different slips. This may be okay at slip equal to 0. At slip equal to 0 or at starting, at slip equal to 1, that is at starting there is no problem. At starting the reaction of the rotor is same for forward and backward field, stator fields. So, the point is here what we assume is the air gap field we assume to be constant. This is assumption here. In a what do you do in a normal 3-phase motor? In a normal 3-phase motor, your air gap field is assumed to be constant at all slips, isn't it? Okay, so what this assumed was, say if you say the flux, air gap flux here the forward and it is air gap flux here backward and both are equal, this flux and this flux, because they are applied with the same voltage. Okay. And you should know that the flux is always proportional to voltage and MMF is always proportional to current, right. MMF that is produced is proportional to the currents carried or a magnetizing current, whereas air gap flux is proportional to voltage applied. Why? What is the relation? You must remember that voltage is equal to 4.44 F into N into phi. So, so long as you maintain the voltage and frequency constant, your flux will remain constant, right. You are applying almost neglecting the series drops, etc. Therefore, I am trying to emphasize this, that in a 3-phase induction motor, throughout the operation, so long as the voltage and frequency is constant, air gap flux per pole is constant, only that flux per pole is rotating. It is like you are spinning a fixed magnitude magnet in the rotor, that is what it means. Air gap is like you are spinning a magnet, but magnet is not changing its strength. Is that clear? Okay. Because from your reaction I am feeling just like rotor reaction unequal, your reaction is also not very positive. Okay. Is it clear? Any doubt on this? Right. So, that was Ferrari's concept. He said it is like two air gap rotating fluxes. Rotating field means he meant rotating fluxes. But then the Steinmetz, he gave a new concept. The Steinmetz, that was in 1898, that was in 1894, this was in the transaction of American Institution of Electrical Engineers. You can imagine we are talking about 108 years old story. Now, okay, it was 1898, in this paper Steinmetz gave what is known as a cross field theory. Which is now popular known as DQ theory. He said single phase machine has to be resolved into two fluxes at quadrature and analyzed appropriately. You have DQ model. If those who have studied the modeling of machines, they know what is known as a DQ model, and you can write down those DQ equations to get the solutions, okay, and which gave the correct concept. Okay. The problem with this model was the whatever the current that was carried here was not the same as the cumulative current of both the systems, even though the you make the flux to be half of this. If this is the flux phi, this flux is supposed to be phi by 2, this flux is supposed to be phi by 2, right. If the single phase motor was having a flux phi per pole, this should be phi by 2 phi by 2. Okay. Now, but this current was not the same as the total current carried by both the machines, and this heating here was the heating here was much more than this, right, and the torque was different at other slips, right. So, this created the problems, and that is why the cross field theory came. Now, as an explanation to this, it was Kennelly in the same paper, as a comment to the same paper 1898, said it is possible to explain the single phase machine with rotating field theory, provided we do not assume the rotating fluxes are same, but we assume what is same, rotating MMF same. So, rotating stator MMF phi s plus will be equal to phi s minus. Okay. So, that was the whole concept that we had to take care of. Okay. Now, this was the thing. Then how do you explain this now? Can we write down? You have this one, sorry, we have this one machine, okay. Right. So, what you can do is the same thing, instead of connect them in parallel, you connect them in series. Okay. So, let us say from A phase it goes to A winding, okay. This is the other A winding, okay. Now, the other one is B winding, comes here, but the B wind is connected to the C here, supposing ABC here and ABC here. So, you have connected the other way around, and similarly for the C winding, you connect it to the B winding. So, in this case Fs plus equal to Fs minus, but phi plus is not equal to phi minus, right. So, if you connect the stator like this is the correct way. So, that means the stator winding should be connected in series and not in parallel. If you connect them in series, so here this is your Fs plus and this is your Fs minus. Since the same current is flowing through, after all same current is flowing through, only thing is you have made the stator MMF opposite by connecting in the opposite way like this. Okay. So, this is the Kennelly's connection. Or a series connection. So, we said that if you have the flux constant, you have one type of a curves for torque versus speed. Okay. This is flux constant. So, this flux is constant to this same flux, okay, and you have a resultant, say something like this. This is the net torque, this is T forward, T backward. Throughout the flux is maintained constant. That is the one model which is not correct. Then the other model was, you do not keep the flux constant, so here the Fs plus equal to Fs minus, and phi plus is not equal to phi minus. Is it okay? It is this connection, in which case your net torque will be something different. Sorry. This is the torque. Okay. Now, you are getting more torque in the forward field than the backward, because rotor reaction was different. Rotor reaction was different other than at starting. So, at all these points you would find that phi f was more than phi b at all other speeds, because why? Why the forward flux per pole was more than the backward flux per pole? Because flux is due to the combination of stator MMF and rotor MMF, okay, and the rotor MMF was weaker, okay, rotor MMF was in a way that it would enhance the forward flux, okay, and it would reduce the backward flux, because rotor current due to backward field was more because of larger slip. Okay. Therefore, this was the condition. So, you will notice therefore certain, so you will still get T start equal to 0, starting torque is 0, okay. Then what do you have? You have another feature, that at synchronous speed, what do you notice at synchronous speed? There is a negative torque at synchronous speed, that is what you notice. And third one, you notice that there is another point of 0 torque. Is it at synchronous speed? Here T is 0 and the N is less than synchronous speed, and this is your synchronous speed. So, these are some features that you will notice, and you will also notice that the maximum torque, this is the maximum torque, occurs at some point which is at a lower speed than what it would occur if only forward field were there. Okay. So, the single phase motor, you will notice the maximum torque occurs at lower speed, the slip at maximum torque is is at a different point, and the starting torque is 0, and you will notice that there is a 0 torque at a speed slightly less than synchronous speed, and at synchronous speed the torque is not 0, but it is negative, because the torque is 0 only due to forward field at synchronous speed, but there is some negative torque due to backward field. So, these are some of the observations that we can make on the single phase induction motors. Okay. So, to sum up, we have already done that forward and backward rotating flux equal at all speeds. This is a wrong assumption. Okay. Then this was when flux is constant. This was what is known as the Ferraris model, and which was not correct. Then we said that Fs plus is equal to Fs minus, only the stator MMF is valid. Then rotor MMF opposes stator current. So, there is a reduction in backward flux wave and aiding in the forward flux wave. That means, in the air gap you see the forward, that means there is a, if you look at a forward rotating magnet, it is a stronger magnet than a backward rotating magnet, unlike in the double revolving field theory where it was assumed to be same magnet. Okay. So, that will change at different speeds. Okay. So, forward torque will be of the motor increases. Okay. So, we have a better characteristics. So, here is Fs plus equal to Fs minus. This is what we had come to the conclusion. I am slightly emphasizing this, spending some more time, because I think you have to be very clear. At this point, if you are not clear, you let me know. Clear? So, it is just simply that the stator surface is magnetized differently and rotor surface is magnetized differently due to the respective excitations. Okay. So, therefore, it does not have a starting torque, therefore, you must give a starting torque. Initial deflection is required to start the motor. So, initially you must start, but there is a running torque. As soon as you start, there is no problem, it will run. Okay. Therefore, initial deflection can be provided. That means, you must at starting you must make the forward field stronger than the backward field. Okay. So, you must have a revolving field produced by two phase windings carrying two phase supply. So, the basic principle is at start make forward field more than backward field. That is your principle of starting. Somehow make it in such a way that starting you have a stronger forward field than the backward field. Okay. Then it will give a, therefore, there is a, so T forward will be more than T backward. So, T starting will become positive. Okay. So, how to make, next our question is, what is the mechanism in which you can make the forward field stronger. Okay. So, for this the procedure that is used is use two windings. One is the main winding, another is the auxiliary winding. There are two windings are there and they are at quadrature. Okay. So, you have two windings. Okay. Now, if this is leading, this will be the auxiliary winding, this will be the main winding, because A leads M by normally 90 degrees. They are wound in such a way that auxiliary winding leads the main winding by 90 degrees electrical. So, you have to wind it. So, it is called a, therefore, you have a two phase winding. So, use the two phase winding, that is what we should do. Okay. Now, just placing two phase winding will not do, you have another requirement. say you make I at the auxiliary winding lead I at the main winding. This is also important, because you know that just two phase winding, if they carry the same current, it will not of any use, it will give again a pulsating field. Therefore, if this is I A, this should be I M or whatever it is. So, it should be leading, preferably 90 degrees. But even if it is not, but still it will create a forward field. Okay. Desirable 90 degrees, okay. But even if it is 40 degrees, it will still produce a forward field. Okay. Windings would be at ideally, if you do not want any negative field at all, what you should do? Ideal condition. Ideal should be the MMF of the M winding should be same as MMF of the A winding. That means Nm Im should be equal to Na Ia MMF, and Im leads Im lags Ia by 90 degrees in time. Only then it will be pure forward field. You will have a pure forward MMF. There is no backward field at all, because you know in a 3 phase winding carrying 3 phase balance current give you only forward field and no backward field. So, similarly 2 phase winding carrying 2 phase currents will also give only forward field and no backward field, is not it? I hope this basics you have not forgotten. Okay. 2 phase winding, after all you can create purely forward rotating field by any M phase winding carrying M phase currents. It need not be 3, it could be 4, it could be 5, it could be 6 or 10 or whatever it is, so long as you can produce these multi-phase currents. That is why people are now talking of multi-phase windings, because your power electronics can give you any phase currents. Okay. By a DC you can create any phase, not necessarily 3 phase, you can have 5 phase, 6 phase etc. Okay. So, this is one thing you have to produce to start the machine. So, the principle is starting of single phase motors, you need a 2 phase supply is to be obtained by splitting the phases, and then you have 2 winding auxiliary winding to be used to aid in producing the starting torque. So, whatever I said, agreed? Therefore, the main and auxiliary windings are supplied by currents in almost quadrature to produce starting torque. So, they must carry currents nearly in quadrature. Of course, after the starting, either the auxiliary winding can be removed also, you do not it has no purpose. Okay. So, you make it in such a way, so auxiliary winding can be wound for short time duty, it need not be wound to carry full current for all the time, and you can disconnect them. Okay. And disconnection we have seen that there is what is known as centrifugal switch, it is a mechanical arrangement in which it can be automatically disconnected, because nowadays you can think of electronic switches etc., but as of now nobody has produced a switch which is cheaper than a centrifugal switch. Even electronic switches to disconnect tend to be costlier than a mechanical centrifugal switch. Okay. Now, normally the starting torque depends upon the extent of phase splitting, okay, and is proportional to sin theta, where theta is the angle between the main winding current and auxiliary winding current. So, typically this T starting will be proportional to sin theta, where theta is the angle between main and auxiliary winding. So, when will you get the maximum starting torque? When theta is 90 degrees. Any other angle it will be less, right. So, one way is you have two windings, split phase motor, but impedances are different. So, you have the Z main is different than Z of the auxiliary winding, that is one thing. So, they carry different currents, same supply voltage V, okay, and this will be the main winding current and this will be the auxiliary winding current. Okay. Now, you want this to carry a leading current, this I auxiliary must lead I main. So, what do you do for the impedances? Huh? What will you do here? What can you do if you have only two windings to do? You are splitting phases, two windings are there. You have got you want to do you, what design changes you make in this? Two windings cannot have the same impedance, isn't it? If you have the same impedance, they will carry the same current and same phase angle. But you want a phase splitting, phase angle must be different of the IM and IA. What do you do? No, I am not allowing you any capacitor here. Capacitor is, this is no capacitor here. Huh? Pardon?
Impedance of the both windings are different.
They are different. How much? What should it be? You know, impedances have certain. You know, what do you mean by impedance? It has its own. Say, what will be the? See, you have Z main will have some R main plus J times X main, and Z auxiliary will have its own resistance RA plus JXA, let us say. Okay. Now, if you want IA to lead IM, what should be the relative magnitude of these impedances?
RA greater than R.
So, you want RA should be more resistive, this should be more resistive, this should be more inductive, is not it? So, here RA must be greater than RM. That means, you wind the auxiliary winding with thinner wires, longer wires, more turns and so on. Okay. And another thing you would prefer is what are reactance? XM must be, so you must design it in such a way that the impedances are different. Therefore, you will invariably find for the same voltage IM will be lagging more than IA. Both will be of course lagging, because it is more resistive. So, this may be phi A and this may be phi M, right. I think it is very simple circuit theory. You make one more resistive than other and you get the, this is a split phase machine. So, you will get some starting torque. This is one of the simplest way to do this. So, in the split phase motors, the phasor diagram, you have this same voltage I auxiliary, I main, and total current will be I. Okay. But if you disconnect that, because this current will not be same, you know, and other slips current will be different. Okay. So, you may have a, if it is a normal single phase machine, if you have these characteristics, supposing this transmit characteristic of this is single phase, okay, and if it is a split phase, it will have some starting torque. So, it is possible it will go something like this, right. This is for split phase. Okay. Two winding you have this characteristics and one winding this characteristics. And of course, after some time you operate a switch, isn't it? Switch means you remove the second winding. So, what will happen? Maybe at this point you remove. What will it do? It will go to the, if you switch, this is the switch. That means you disconnect the second winding. So, it will follow the torque speed characteristic of the first winding, right. This is the point of switch. At this speed, let us say centrifugal switch will operate when it reaches near synchronous speed. Okay. Is it clear? So, the net characteristics will be as mentioned here. It will follow, so somewhere it will follow this. The total characteristics, split phase. Okay. Right. Now, next other way is, as you can connect a capacitor in the auxiliary winding, because then you do not have to bother too much about your design of the second winding. So, in fact, second winding can be similar to the first winding, because since you are connecting a capacitor, you have less of a problem. Okay. Therefore, here your auxiliary winding will be, since it is capacitive, it will have a leading current than the main winding, and you can adjust in such a way that this can be nearly 90 degrees. Auxiliary current will be leading the main current, though they may not have the same number of turns, but they are wound to have this in such a way that they will lead by 90 degrees. Okay. Any doubts on this? So, we have created another arrangement, and so here also, if you have the torque speed characteristics, if this is single phase, one winding, and again you may have two windings, okay, with capacitor, and you will, if you have the, if you operate the switch here, switch operates here, and it is easy to see that the net characteristic, it will start initially, it will follow these two winding characteristics, okay, and after the switch operates, second winding is disconnected, it will follow the one winding characteristics, that is here. Okay. So, this is the net characteristics. Is it clear? So, at starting it follow the two winding characteristics, at running it will carry the one winding characteristics. Of course, whatever I am explaining now is more a qualitative explanation. Okay. We will go into more quantitative one subsequently. Okay. Then other way is, do not disconnect the second one, keep it permanently, how does it matter? Okay. So, it is that means you have a, what is the difference between the earlier one and this one? What are the differences that you will see? In this winding, if you want to make a, these are like fans, your ceiling fan has this one. These ceiling fans have capacitors connected permanently. Now, you tell me what a designer should take care with reference to the earlier one where second one is disconnected. If you have to design both the motors, one time is capacitor start only, another is capacitor run. Hmm? Is there any precaution or any factors he has to consider?
So good induction, this auxiliary winding should be of good quality.
Auxiliary winding should be capable of running full time. So, your fan you want throughout the night to operate, whereas in the case of starting only you can make a cheaper or a low capacity winding, because how do you design it should withstand the heat, right. If it is only for a short time, a small wire will do, thin wire will do, but if it is full time it should be capable, it should be designed with proper capacities. So, every copper wire will have what is a short time rating and a long time rating. Okay. After all, if you have a small wire, it can carry 100 amperes maybe for a fraction of a second, but it can't carry it for all the time for an hour. If it has to run for an hour, you must use thicker wires. Okay. So, that is the main difference, what is short time rating and a full time rating, okay, continuous rating. So, this is what we had to do. Okay. So, here you have again the characteristics. If it is one winding, you have these characteristics, and you have both the windings, you have a better characteristics. Plus capacitor, 2 winding plus capacitor. Okay. Obviously, used here there is no switch coming into the picture at all, right. Then there is a third way, yeah.
I think the initial condition will not change
Pardon?
in both the cases.
Huh? Yeah, that is true.
But okay, then its design was
Yeah,
different.
but it should be the in a first case auxiliary winding carrying that starting current for a short time, where as soon as you switch disconnect it, it is not carrying a current, whereas in the case of the second case where even it is fully, it is also continuously carrying current and producing its own torque. Okay. The third one is you can have a capacitor start, capacitor run. Okay. So, this is a start switch. Okay. Then initially what will happen? You can have the total capacitor will be, so let us say C1, if say C1 C2. So, C at start what will be capacitor? C1 plus C2. At run it will be C1 only, is not it. So, the C2 is usually you require a higher starting capacitor than a running capacitor. Therefore, you have 2 windings, but here again both windings must be made fairly robust, because they will always be carrying current. Only the capacitor you can adjust, because the same capacitor, why do we need to go to this compared to the second model which we said, why do we have to go? Second model would have been all right, yes.
At the starting we are putting whole of the load in a one capacitor, so that should be of very good quality. But if we are distributing in 2, then initially we can have a low quality capacitor both, and then for the running purpose we can have one.
Yeah, that is one logic. There is also one very important thing, for a best performance, for best performance, C starting is higher than C running. Okay, you need one capacitor to start, another capacitor to run, is not it? Okay, the starting capacitor will not be same. So, if you that means if you have a continuous running system or a single capacitor, it should be a compromise between the two. It is not the one which will give you the best performance both the starting and running. Therefore, the third model is better than the second one, because you have an option for choosing the capacitor values most suitable for starting and most suitable for running. Okay. and then starting capacitor may be of a lower short time rating, and running capacitor must be for a continuous rating. Okay.
So when the motor is running, why the running capacitor is needed for power factor improvement or somewhere else?
No. You see, the running capacitor is because here running capacitor is required because you are designed the motor to give a good torque with both the windings in operation. Now, it is both capacitors are running, both windings are carrying current, both are starting and at running here. Is it okay?
So why do we need higher capacitor
I-
at starting?
He
More torque.
because impedances are different at different speeds. So, you want a good balance of the winding currents, right, and the starting capacitor capacitors are starting. After all, to make a balance, what is your objective? Your objective is to see that both the windings carry balanced currents, isn't it, at quadrature 90 degrees. You can discuss it when we go little more theory into these two winding systems. And you want I auxiliary must lead I main by 90 degrees, okay, and same capacitor will not do at all speeds. Impedances will go on changing with, after all, impedance of the motor goes on changing with slip, right. When the motor impedance changes, whole your system currents will be different for main and auxiliary winding, okay. So, that is the problem. Therefore, if you want to have a characteristics for two capacitor one, say you have one characteristics, say this is for starting capacitor, okay, this is with C start, and you may have another characteristics with C run, okay. I am just giving you some hypothetical curves. So, two characteristics, and you have a switch which will operate somewhere, is not it? This is switch. Switch operates. Therefore, it is easy to note that your characteristic will start from the T start and then it will come to T run. Is it okay?
I think in the starting for C, starting torque should be more, right?
Yeah, started more, yeah, that is right. So, you can even have a, yeah, in fact that is what you expect anyway. Let us see, let's see. So, it can have some better characteristics, not this, okay. Let us see we can. Okay. Now, is it okay? So, we have just made different mechanism of static methods, right. Now, there is also another one which also shaded pole motor, where the two windings are produced, it is what is a pseudo rotating magnetic field, and where pseudo revolving field is produced by using a shading coil on the stator poles. In fact, constructionally, so you have a shading coil, short circuited copper strip wound over 1/3 of the pole face. Okay. The shading coil produces variation instantaneous flux caused by stator winding and gives illusion of rotating magnetic field. Okay. So, it is typically, I wish we had a you have a norm, of course, squirrel cage rotor anyway is there, and you have a normal winding, main winding. right. So, it will produce a main flux. Then what you do is you just make a small cut here in 1/3 of the space and here okay, and you have a you make a small strip just make a ring, this is called shading ring, and you make it here also. So, this is also a shading ring. Now, what will happen is while this is produced, this will induce a current here, after all this is a fluctuating thing. So, this will carry a current and that current will not be in phase with this current. Okay. So, there will be, let us say, I shade so I of shading will be lead I of the main winding. So, this current and this current will be phase shifted. So, all you need is a little, that should be enough to produce a forward torque. All you need is 2 windings carrying 2 currents which are not in phase. So, you have 2 windings, okay, which are not aligned, because this is the main axis, this is shaded axis M and S. So, there is always a phase shift in the position, is not it? The winding axes are different and currents are also different in terms of the induced currents, etc. Okay. So, this is again, this is quite used in most of your table fans, etc. So, that is, it will have some characteristics like this. This is the torque speed characteristics for shaded pole motors. Okay.
Any advantage of these type of motors as compared to the capacitor type motors?
Very simple to make. I mean, advantage is, after all, when you go to buy something, what will you ask for? How much does it cost, right? Customer wants 2 things, one is the cost, another is quality, and this is cheapest. You do not have to do anything, you just put a ring over there, that is all, no capacitor, nothing, because then you have to, and simple to make. Shaded pole motors, what is there? Squirrel cage is there, and
It's all small size,
Huh?
so you can use in relays and all.
yeah, all small motors,
Why not being used in the ceiling fans?
they are used in table fans. Ceiling fans you can try, but ceiling fans, the thing is, it must develop enough of starting torque. Okay. See, after all, engineering is all about compromises of designs. I mean, after all, you can always say why it was not used. There are, because of various experiences. You see, this poor fellow cannot give too much of starting torque. Shaded pole motor, it's just a little starting torque. Ceiling fan, you have big wings are there. It has to have a start. It must give you enough this thing. So these are the various things. Okay, you go to a shop and you ask for coconut oil, and if he says no, I will give you the sarson ka tel or something, because you have gone for a purpose, right? Everything is for a purpose. I mean, why the shaded pole cannot be used? You can use it, but it won't run. So there is always a necessary starting requirement, starting torque, etc. Okay. So I think we can stop here. So we have given a general picture of the theory, but as of now we have not gone into the mathematical modeling and theory. Next we have to go into basic analysis of single phase motors, that we will do in the next class.